forces at an angle, you're going to use the same procedure. You're going to draw a free body diagram correctly. Again, do not add additional forces if they are not present. The only difference you're going to do is any vector, any force vector that is at an angle, you're going to resolve into x and y component using cosine and sine. After that, you're going to write a sum of fx and a sum of fy equation. Remember all the x vectors, you write a sum of fx. All the y vectors, you write a sum of fy. And the same three equations apply. F net is equal to ma. Friction is equal to mu n. And then weight, or F subscript g, is equal to mass times gravity. And then there are two types of angle problems that we are going to discuss. One, they're going to be on ramps or inclines, hills, mountains. And the other ones are going to be just hanging objects. So far we did objects on flat surfaces. When objects are on flat surfaces, the horizontal is your x, your vertical is your y, just like in math. So flat surfaces, we are discussing objects that are on the horizontal surface, so like a box on a flat surface. So my weight is going down, perpendicular to the earth. Normal, which is perpendicular to the surface. So if you notice, N and W, normal and weight, are in the vertical direction according to my x coordinate system here, x and y coordinate system. Another flat surface might be a wall. If I have an object on a wall and it's hanging, I'm going to have weight going down, but my normal is going to be perpendicular to the surface and it's going to go to the right. And then it could have other forces like friction, applied forces, tension. But if you notice, my n is in the x coordinate system and my y is in the vertical coordinate system. Inclined planes or ramps, the x and y rotates. So what happens is the plane of the incline is your x and the y is perpendicular to the surface. So if I have an inclined plane that looks like this, my weight is again perpendicular to the earth. Because if I look at that inclined plane, this is my ground here. So it is perpendicular to the earth. My normal is defined as perpendicular to the surface. Since this is my surface that the object is on, this is my normal. So if I look at my n vector, my normal vector, you will notice it is in my y coordinate system. My w, if you look at my w, my weight, it is at an angle to the coordinate system because this is where my w is. Since my w is at an angle, the first thing I need to do is make it into x and y. Remember, we can only add vectors if they're parallel to each other, or use Pythagorean theorem if they are perpendicular to each other. To make my weight into x and y, I take my normal vector and I extend it back until it makes a right triangle. When I do that, you notice the weight goes down, so my WY will go down. My WX will go down the ramp. Remember, tail to tip. So if the angle for the ramp is given as theta, that is the same angle that is made by my weight vector due to similar triangle. So using sine and cosine, I'm going to divide my WY, or my weight y component, and my x weight component using sine and cosine. Since WY is next to theta, this becomes W cosine theta. My WX is opposite, so this becomes W sine theta. We could redraw the ramp going in the opposite direction. So if I draw the ramp in the opposite direction like this, and we said it only has weight and normal, weight due to gravity, normal because it's on a surface, the x and y coordinate is still rotated because this along the plane is my x, perpendicular to the surface is my y, and the y axis. So that tells us our weight is at an angle. So I need to resolve this into x and y. So again, I take my normal, extend it back until it makes a right triangle. Since my weight vector goes southeast, my WY is going to go to the south. My WX is going to go to the east. Due to similar triangles, this theta and this theta are the same. So WY becomes W cosine theta because it is next to. WX is W sine theta because it is opposite. So if I look at this first problem, we know that this is on an inclined plane because it told you it is 30 degrees from the horizontal on an inclined plane. So if I draw my inclined plane, this is 30 degrees and I have a trunk on my inclined plane. We know there is weight because it is perpendicular to the earth. We have normal because it's on a surface perpendicular to the surface. As we stated, along the inclined plane is our x coordinate system and our y is perpendicular to that. So this tells us weight is at an angle. So I need to resolve my weight into x and y. So I'm going to take my normal vector, extend it back, and make a right triangle. My WY is going to be down. My WX is going to go down the plane. If I do tail to tip, starting from here, tail to tip, the resultant is from the origin to the tip of the last vector. Remember, the weight is the resultant vector, and we're breaking it up into WY and WX components. So this angle here is also 30 degrees because it's similar triangle. So WY becomes W cosine theta because it is next to. WX becomes W sine theta because it is opposite. After we resolve our vectors at an angle, we're going to write a sum of fx and a sum of fy. My sum of fy, remember, this is y, so that is my n. and wy. So n is going up, so it's n minus wy is equal to ma. It is not accelerating in the vertical direction. So this is equal to 0. So I need to add a wy to both sides. So n is equal to wy. If you notice, n is no longer equal to weight. It is equal to wy, which is weight times cosine theta. It is only equal to a component of the weight, not the full weight. This is why it's easier to push or pull objects up and down a ramp, because we don't apply force to the entire weight. If I write a sum of fx equation, the x coordinate system is this, which is parallel to the inclined plane. The only vector that is parallel to the inclined plane is this right here, the wx component. So fx is equal to wx equals to ma. And we know ma is not equal to 0 because we are determining the acceleration of the trunk. So what is wx? We solve wx as w sine theta, so I'm going to plug that in. This is equal to ma. What is w? In the previous videos, we learned that weight is equal to mass times gravity. So I'm going to substitute in for weight, which is mg sine theta equals to mass times acceleration. If you notice, the masses cancel out. I have a mass, so I divide here. I have a mass here, I divide here. This tells us acceleration is just equal to g sine theta, in which g is 9.8 meters per second squared times sine theta, which is 30 degrees. And if you plug this into your calculator, you should get around 4.90 meters per second squared. This problem tells us that the object's mass doesn't determine the acceleration. Only gravity and the angle will determine the acceleration. Pause the video, read the question, draw your free body diagram, write your sum of fx and sum of fy equation, and check your answer. We know this problem is very similar to an incline or ramp problem because the cover is lifted in a book to make an angle, similar to a ramp. So if I have a coin here, the forces I have, again, are weight perpendicular to the earth because we can't turn off gravity on earth, normal perpendicular to the surface, and then we also have friction. We know we have friction because it asks us to look for the coefficient of static friction. If there was no friction, this object will move down the ramp. Since this object will move down the ramp, friction needs to oppose the motion, so it must go parallel up the ramp. So, according to our coordinate system, x is parallel to the inclined plane, y is perpendicular to it. So we know my weight vector is at an angle. So I'm going to take my normal, extend it back, make a right triangle. This is going to be wy, this is wx, wy is going to go down, wx is going to go down the inclined plane. If it wasn't for friction, it is the weight component that's making the object go down the inclined plane. So the angle here is 38. Due to similar triangles, this is also 38. So we know that theta is next to wy, so that's going to be w cosine theta. Theta is opposite wx, so that's going to be w sine theta. Now I'm going to write my fy equation, my fy equation is equal to n going up minus wy going in the opposite direction. This is why we put the negative sign in. This is equal to ma. So if I look at my coordinate system, this is my y. The vectors in my y direction are n and wy. This is why it's n minus wy. It is not moving in the vertical direction, so ma is equal to 0. So that tells you n is equal to wy if we rearrange it. In the x direction, this is our x direction. In the x direction, we have friction because it's going along the plane, and we also have wx. We're going to do the same thing as before. We're going to write a sum of fx equation. The direction the object is moving is going to be positive. Since the object wants to go down the ramp, wx will be positive, so we're going to write wx. Friction is in the opposite direction, minus f. This is equal to ma. My ma is equal to 0. Why? The problem says just begins to move. So to just begin to move, it needs to overcome static friction. So now my equation is wx minus f equals to 0. I'm going to add a friction to each side. So wx is equal to friction. And what did we say friction was equal to? Generic formula for friction is mu n. So wx is equal to mu n. And what is n equal to? wy. So wx equals to mu wy. So I'm going to divide both sides by wy to get mu. So mu equals to wx over wy. I'm going to substitute in for wx. Wx, remember, was w sine theta divided by wy, which was w cosine theta. If you notice, w cancel out. You could plug in sine 38 divided by cosine 38, but a sine theta over a cosine theta is a tangent theta. So this is equal to tan 38. If you do the math correctly, you should get 0.781.